Biscuit Basin, Yellowstone National Park, Wyoming, July 23, 2024. Shortly before 10 in the morning, a Tuesday, the park is busy. Biscuit Basin is one of the most accessible hydrothermal areas in Yellowstone, a short walk from a parking lot. A cluster of vivid hot springs and geysers connected by boardwalk, the kind of place where families stop for 20 minutes, take photographs, and continue toward Old Faithful. The basin sits about 2 miles northwest of Old Faithful, in the Upper Geyser Basin, one of the most thermally active regions on the continent. Visitors are on the boardwalks. Then, without any warning that anyone on the ground or in the monitoring network had received, the ground beneath the basin erupts. Not a volcanic eruption, a hydrothermal explosion. The source was Black Diamond Pool, one of the thermal features in the basin. Superheated water that had been sitting at shallow depth, maintained in liquid form only by the pressure of the rock above it, flashed rapidly to steam. The expansion was immediate and violent. Black water, mud, rock, and debris were thrown an estimated 400 to 600 feet into the air, based on later analysis of photographs and video. Sections of boardwalk were destroyed. A bench and portions of fencing were torn apart. Debris was scattered across the surrounding area. 400 to 600 feet is worth picturing. That is the height of a 40 to 60-story building. A column of dark, scalding water and rock, taller than almost any structure most of the visitors had ever stood next to, rising out of the ground in seconds where, moments before, there had been a placid blue hot spring, ringed by a wooden walkway. The videos that visitors managed to capture as they ran show exactly this. A sudden, towering eruption of black material against a clear summer sky, and people scrambling backward along the boardwalk as debris began to rain down around them. Nobody died, not because of a warning, not because of a prediction, not because the monitoring network had seen it coming, but because of timing, because the visitors who were on the boardwalk happened to be far enough from the precise location at the precise moment. The ground gave way to scramble clear. It was, by multiple accounts, a close call. Scientists analyzing the seismic and acoustic data that recorded the event would later confirm what their instruments captured. There were no precursors detected by the monitoring instruments. The explosion simply happened. The instruments had been there. Hydrothermal explosions had been happening in the Yellowstone region throughout the geological record. Hundreds of them over the past several thousand years. This one became one of the most thoroughly documented in real time. And nobody, not the monitoring network, not the scientists, not the park rangers, not the visitors who had walked those same boardwalks minutes before, had received any warning that it was coming. That is the part of the Yellowstone story that most coverage never tells. Not the supervolcano, not the civilization-ending scenario, not the probability statistics about a geological event that might happen tens of thousands of years from now. The explosion that happened in a tourist area without warning in July 2024, in a place where millions of people per year walk across the ground. Every documentary about Yellowstone starts with the supervolcano, the Overdue eruption, the civilization-ending scenario, the magma chamber that could unleash a catastrophe visible from space. And every one of them buries the part that is actually true, the part that is actually happening, that has been happening for thousands of years, that happened again in the summer of 2024. The real story of Yellowstone is not about what might happen someday. It is about what is happening right now. Beneath the geysers and the hot springs and the boardwalks, a geological engine is running. It has been running for roughly 17 million years. It breathes in and out, inflating the caldera floor by centimeters, deflating it, shifting, seismic, following rhythms that no human timescale can fully comprehend. And occasionally, it reminds us that it is there. This video is about Yellowstone, not just the supervolcano, though we will address the supervolcano honestly. including the actual probability numbers that most coverage either exaggerates or never quotes. Not just the geysers, though they are among the most extraordinary natural phenomena on the North American continent. And not just the doomsday scenario, which is technically possible in the same sense that a large asteroid impact is technically possible, which is to say, real, documented, and vanishingly unlikely on any human timescale. This video is about what Yellowstone actually is. It is the current position of a geological hotspot that has been burning through the North American continent for roughly 17 million years, leaving a trail of calderas and volcanic features hundreds of kilometers long across what is now parts of Nevada, Oregon, Idaho, and Wyoming. It is one of the largest hydrothermal systems in the world, with more than 10,000 thermal features, hot springs, geysers, fumaroles, mudpots, concentrated within the park's boundaries. It is a caldera, formed by one of the largest volcanic eruptions of the past 2 million years. So enormous that most visitors walk across its floor without realizing they are inside a volcanic structure. And beneath it, at depths of several to many tens of kilometers, a magmatic system of extraordinary complexity, mostly solid, carefully monitored, not showing any signs of impending eruption, is being watched continuously by one of the most sophisticated geological monitoring networks ever deployed on Earth. By the end of this video, you will understand what Yellowstone actually is, what is actually happening beneath it right now, what the real hazard spectrum looks like in order of probability, what the July 2024 explosion revealed about the limits of prediction, and why the honest version of the Yellowstone story, without the doomsday exaggeration and without the dismissal, is more interesting than either extreme. So, what exactly is Yellowstone, and what is actually happening beneath it right now? How big was the July 2024 hydrothermal explosion, and how close did it come to killing people? How does the monitoring network that watches Yellowstone actually work? What can it detect? What can't it detect? And what would it show in the weeks before a major eruption? What are the real hazards at Yellowstone in order of probability? And how do they compare to the supereruption scenario that gets all the attention? What is a hotspot? And how has Yellowstone's hotspot been moving across North America for millions of years? And what does the geological record of Yellowstone's past, 3 supereruptions, hundreds of hydrothermal explosions, decades of ground breathing and shifting, tell us about what to expect from its future? This is not a doomsday video. Yellowstone is not about to erupt. There is no elevated alert. The Yellowstone Volcano Observatory, which monitors this system continuously with roughly 50 seismometers, GPS stations, gas sensors, infrasound and acoustic detectors, and satellite-based thermal imaging, maintains a normal alert level and a green aviation color code as of early 2026. The magma chamber beneath the caldera is mostly solid, not a seething pool of lava waiting to explode, but a region of partially crystallized rock with a melt fraction of perhaps 5 to 15% distributed through it. The annual probability of a caldera-forming supereruption is estimated at roughly 1 in 1730,000, comparable to, or even lower than, many natural hazards we rarely think about. The USGS itself says this estimate is probably an overestimate for the short term, and adds that scientists are not convinced another supereruption will ever happen at all. But this is also not a video that dismisses Yellowstone as nothing but a beautiful national park with an exaggerated reputation. The July 2024 hydrothermal explosion happened in a tourist area, without warning, and would have been dangerous, potentially deadly, to anyone in the immediate blast zone. The USGS identifies hydrothermal explosions as the geological hazard most likely to impact people in the park. The monitoring network, for all its sophistication, did not predict this event, and the geological system beneath the park, the breathing caldera, the seismically active crust, the hydrothermal plumbing that connects thousands of surface features to a magmatic system kilometers below, is genuinely extraordinary, genuinely active, and genuinely deserving of careful attention. The honest version of this story is more interesting than the doomsday version. Stay with me. Before we go deeper into the geology, if these are the kinds of stories that pull you in, real Earth science told honestly without the doomsday exaggeration and without the dismissal, hit subscribe. Galaxy Pulse goes beyond the headlines every single time. We will not tell you civilization is ending when the scientists say it isn't. But we will tell you what the ground beneath Yellowstone is actually doing, and it is more interesting and more surprising than most coverage captures. Now, back to Yellowstone, and to the geological engine that has been running beneath it for millions of years. To understand what Yellowstone is, and what the real hazard picture looks like, we need to start where the story actually begins. Not in the park itself, but in the deep mantle beneath it, where a column of anomalously hot rock has been rising, driving a geological engine that has been reshaping the western United States since long before any human was here to observe it. And we need to understand what that engine has produced, not just at Yellowstone, but across a trail of volcanic features hundreds of kilometers long that stretches from the Nevada-Oregon border to Wyoming, each one older than the last. Each one a reminder of where the hotspot was before it was here. There are different ways for a volcano to exist. The kind most people picture, the cone-shaped mountain, the flowing lava, the explosive eruption, is the subduction zone volcano. These form where one tectonic plate dives beneath another, releasing water from the subducting rock into the overlying mantle and triggering melting. The Cascade volcanoes of the Pacific Northwest, Mount St. Helens, Mount Rainier, Mount Hood, are this kind. The Andes, the volcanoes of Japan and Indonesia. They erupt frequently, they are dangerous, and they look exactly like what most people imagine when they think of a volcano. There is another kind, and it sits beneath Yellowstone. A hotspot volcano forms not at a plate boundary, but in the middle of a plate, above a region of anomalously hot mantle, a zone of material that is hotter than the surrounding rock, rising from deep below. As the tectonic plate moves over the relatively stationary hot region, the hotspot effectively burns through successive positions, producing a chain of volcanic features that gets progressively older as you move in the direction from which the plate came. The most famous example of hotspot volcanism is the Hawaiian Islands. The chain of islands, each one successively older to the northwest, is the surface expression of a single hotspot that the Pacific Plate has been moving over for tens of millions of years. Hawaii itself, the youngest island, sits over the active hotspot. The Big Island is still volcanically active because the hotspot is still beneath it. The Yellowstone hotspot works by a broadly similar mechanism, but in a continental setting rather than an oceanic one. And, in a continental setting, the consequences of hotspot volcanism are different, more explosive, more catastrophic on the scale of individual events. Because thick continental crust behaves differently from oceanic crust when intruded by hot material from below. Rising heat melts the continental crust to produce rhyolite, a silica-rich, viscous magma that traps gas and, when it erupts, can do so with enormous explosive force. This is why the same hotspot that produces gentle lava flows in oceanic Hawaii produces caldera-forming supereruptions beneath continental Yellowstone. It is worth pausing on what a hotspot actually is, because the concept is more subtle than it sounds. A hotspot is a region where unusually hot material from deep within the Earth rises toward the surface, independent of the boundaries between tectonic plates. Most of the world's volcanoes sit along plate boundaries, where the logic of where and why is straightforward. Plates collide or separate, and volcanoes follow. Hotspots break that rule. They appear in the middle of plates, far from any boundary, and they tend to stay roughly fixed in place over very long timescales while the plate slides over them. The result is the signature of all hotspots, a trail. As the plate moves, the fixed heat source punches through it at successively different locations, leaving a chain of volcanic features that records the plate's motion like a needle scratching a line across a moving record. Read the trail backward, and you can reconstruct where the plate has been and how fast it has traveled. The Yellowstone hotspot has left exactly such a trail, and that trail is one of the clearest pieces of evidence for how the North American continent has moved over the past 17 million years. There is an ongoing and genuinely interesting scientific debate about the deepest nature of the Yellowstone hotspot, whether it is fed by a narrow plume of hot rock rising all the way from near the boundary between the Earth's core and mantle, nearly 3,000 kilometers down, or whether it originates in shallower processes within the upper mantle and lithosphere. The deep plume model is the classic picture, but the geometry beneath Western North America is complicated, and the question is not fully settled. What is not in doubt is the surface result: a long, age-progressive track of volcanic centers that ends, for now, at Yellowstone. The story of Yellowstone begins roughly 17 million years ago, in what is now the region around the Nevada-Oregon border. At that time, the hotspot was in a different position relative to the North American plate, which has been moving gradually to the southwest relative to the hot region below. The oldest volcanic features associated with the Yellowstone hotspot are in that border region, dated to around 16 to 17 million years ago. Massive eruptions of basalt and rhyolite, calderas that have since been eroded, filled, and buried. As the plate moved over the hotspot's surface position tracked across the continent in a broadly northeast direction relative to the moving plate. The trail it left behind is the Snake River Plain. The Snake River Plain is a broad, flat, volcanic province stretching across southern Idaho from the Nevada-Oregon border toward the Wyoming border. From the air, or from a satellite, it looks like a smooth arc cutting through the topography of the surrounding basin and range mountains, a lowland running northeast across Idaho, bordered by mountains on either side, filled with relatively recent volcanic material. On the ground, it looks like rich agricultural land, fed by the Snake River and the aquifer that underlies the plain. What the plain actually is, geologically, is the track of the hotspot. The successive calderas formed as the hotspot burned through the crust, then filled in and were partially buried by subsequent lava flows and sediments. The volcanic centers become progressively older to the southwest, and progressively younger toward Yellowstone, a series of caldera complexes marking where the hotspot sat at different times over millions of years, until, beginning about 2 million years ago, the activity arrived at Yellowstone. There is something almost poetic about the Snake River Plain when you understand what you are looking at. The farms and potato fields of southern Idaho, the towns and highways, the quiet agricultural land, all of it sits on the healed scars of ancient supervolcanoes. Each of those buried caldera complexes was, in its day, the site of eruptions comparable to the ones that formed Yellowstone. They erupted, collapsed, and then fell silent as the plate carried them away from the heat source. Over the following millions of years they cooled, subsided, were buried under younger lava and sediment, and eventually became the flat, fertile lowland that feeds a significant share of a region's agriculture. The violence is entirely in the past for those older centers. They are, geologically, dead, and their death is exactly what makes them peaceful and productive today. This is the eventual fate of Yellowstone too. The current caldera will, in the distant geological future, become another quiet stretch of cooled and buried rock, while the hotspot continues its slow march to the northeast. This progression, the orderly aging of volcanic centers along a line, is one of the most elegant confirmations of the hotspot model that exists anywhere on Earth. If you date the volcanic rocks along the Snake River Plain, their ages line up almost exactly with the rate and direction of North American plate motion. The hotspot did not move across the continent. The continent moved across the hotspot and left this track as the record. Yellowstone is simply the leading edge of that record, the place where the hotspot happens to be punching through the crust right now. The 3 supereruptions at Yellowstone are the most recent chapters in this long story. The first, about 1 million years ago, produced the Huckleberry Ridge eruption, the largest of the 3. It ejected on the order of 500 cubic kilometers of material, an almost unimaginable volume, and spread ash across much of North America. A caldera formed where the magma chamber collapsed. To grasp what 500 cubic kilometers actually means, it helps to have a comparison. The 1980 eruption of Mount St. Helens, a major, deadly, nationally traumatic event, ejected roughly 1 cubic kilometer of material. The Huckleberry Ridge eruption ejected something like 2,500 times that volume. The 1991 eruption of Mount Pinatubo in the Philippines, one of the largest of the 20th century, ejected around 10 cubic kilometers and measurably cooled the entire planet for a couple of years. Huckleberry Ridge was hundreds of times larger still. These are not differences of degree so much as differences of kind. A supereruption is to an ordinary volcanic eruption what an ocean is to a puddle. This is why geologists reserve the term supereruption for events that eject more than 1,000 cubic kilometers, and why only a handful of such events are known from the past 2 million years of Earth's history. The second, about 3 million years ago, produced the Mesa Falls eruption, smaller, on the order of 280 cubic kilometers, but still enormous by any normal standard, dwarfing any volcanic eruption in recorded human history. A second caldera formed. The third, about 1640,000 years ago, produced the Lava Creek eruption, on the order of 1,000 cubic kilometers of material. The caldera it formed is the one that largely defines the park today, roughly 70 kilometers long and 55 kilometers wide, one of the largest volcanic calderas on land. Much of the floor of Yellowstone National Park is the floor of this caldera. Pause here for a moment, because one thing deserves its own emphasis. The Yellowstone caldera is so large that most visitors to the park do not perceive it. The caldera is not a neat crater with steep walls and a visible floor. It is an enormous sunken region, its edges blurred by post-eruption topography, its interior filled with forests and rivers and geothermal basins, and the Grand Canyon of the Yellowstone. You can spend days in the park without ever consciously registering that you are walking across the floor of one of the largest volcanic structures on the continent. This is a genuinely strange feature of human perception and scale. We are good at recognizing volcanoes that look like volcanoes, the conical mountain, the obvious crater, the menacing peak. We are very poor at recognizing a volcano so large that we are standing inside it. The Yellowstone caldera is tens of kilometers across. From any point on its floor, its rim is often too far away and too gentle to read as the wall of a crater. The mind simply files the surrounding ridges as mountains and the floor as a valley or a plateau, never assembling them into the shape of a single colossal volcanic structure. It is a little like a microbe trying to perceive the shape of the lake it lives in. The feature is too big, relative to the observer, to be seen as what it is. That invisibility is part of what makes Yellowstone so geologically strange. The volcano is everywhere, but it does not look like a volcano. Under normal geological conditions, for a volcanic system in a quiescent phase between major eruptions, here is what you would expect. Minimal seismicity. Background levels of ground deformation. Limited hydrothermal activity concentrated in a few areas. the system cooling and relaxing between events separated by hundreds of thousands of years. Not something you would need to monitor continuously. Not something that would require a dedicated consortium of universities and government agencies watching it around the clock. What the monitoring network at Yellowstone shows, instead, is a system that is constantly active in ways that are normal for Yellowstone, but would be alarming at almost any other geological feature on the continent. On the order of 1/500 to 2/500 earthquakes per year. Most are micro-earthquakes, magnitude 2 or below, imperceptible without instruments. Occasional swarms of dozens or hundreds of small events over days. The largest in the historical record, the 1959 magnitude 7.3 Hebgen Lake earthquake just outside the park, killed 28 people, most from a landslide triggered by the shaking, and permanently altered the behavior of hydrothermal features across the park. The caldera floor has been uplifting and subsiding cyclically for as long as it has been measured. Over the 20th century, parts of the caldera rose substantial amounts over some decades, then subsided in others, then resumed rising, a breathing motion driven by the movement of magma and hydrothermal fluids in the crust below. A notable episode of uplift on the North Caldera Rim began in mid-2025 and ceased in early 2026, which the USGS has described as a subtle change in deformation style that scientists are actively studying. More than 10,000 hydrothermal features, hot springs, geysers, fumaroles, mudpots, are spread across the park. The overall thermal output of the Yellowstone system is enormous, on the order of thousands of megawatts, all of it coming from the earth beneath the park. And in July of 2024, a section of popular tourist boardwalk was destroyed by an explosion that arrived without warning and reminded the scientific community and the public that the hazard most likely to actually affect people at Yellowstone is not the supervolcano. It is the ground beneath their feet. The July 23, 2024, Biscuit Basin explosion deserves the full telling it almost never receives. Biscuit Basin is situated about 2 miles northwest of Old Faithful, reachable by a short drive along the main park road and a short walk across a bridge over the Firehole River. It was named for the biscuit-shaped silica deposits, sinter formations built up over centuries by thermal activity that once ringed its hot springs. The 1959 Hebgen Lake earthquake altered many of those formations, but the area remained one of the park's most visited hydrothermal basins, with clear turquoise and blue hot springs, small geysers, and the vivid colors of microbial mats surrounding the thermal features. Among the basin's features is Sapphire Pool, a large, striking hot spring famous for its deep blue color, the product of light scattering through very clear, very deep water. It has been a photographic subject for generations of park visitors. It is worth being clear about one point that much popular coverage gets wrong. The July 2024 explosion did not come from Sapphire Pool. It came from a different feature in the same basin, Black Diamond Pool, and it was Black Diamond Pool, not Sapphire Pool, that was transformed by the event. On the morning of July 23, the basin had been busy with the usual early summer tourism. Visitors had been on the boardwalks. The morning was clear. Shortly before 10 in the morning, local time, Black Diamond Pool erupted. The event was a hydrothermal explosion, a rapid conversion of superheated subsurface water to steam, driven not by volcanic activity, but by the pressurized hydrothermal system that underlies the basin. The triggering mechanism was not pinned down. There was no obvious precursory signal in the data from nearby instruments. The explosion simply happened, as such events have happened in the Yellowstone region for thousands of years. At the moment conditions crossed whatever threshold separates stable from unstable in the pressurized water system below. The explosion threw a column of black water, mud, rock, and debris, an estimated 400 to 600 feet into the air. A figure derived from later analysis of the photographs and videos visitors captured as they ran. When the material fell, it blanketed the surrounding area and destroyed sections of boardwalk, along with a bench and fencing. The scene visitors encountered in the immediate aftermath was an area of blasted ground, smoking debris, and the transformation of a landscape that had looked the same for generations. Geologists who later examined the deposit found that the ejected rocks were composed of glacial materials, sandstones, siltstones, and gravels. The shallow layers that lie just beneath the silica crust at the surface. None of the deeper rhyolite bedrock, which sits roughly 50 meters down, was found in the debris. This told the scientists something important. The explosion was generated at a shallow depth, within the near-surface hydrothermal plumbing, not from anything deep or magmatic. That is characteristic of hydrothermal explosions, whose conduits mostly exist in the uppermost layers of the crust. This detail is more reassuring than it might first appear, and it is worth understanding why. If the debris had contained fragments of the deep rhyolite bedrock, that would have implied the explosion reached down into the levels where the magmatic system begins to make its influence felt. A more alarming scenario. Instead, the rocks came entirely from the shallow layers, the loose glacial and sedimentary material that sits in the top few tens of meters. The event, violent as it was at the surface, was confined to the shallow plumbing of the hydrothermal system. It was a near-surface phenomenon, driven by shallow water and shallow pressure, with no indication of involvement from the deep magmatic system at all. The composition of the debris is, in effect, a depth gauge, and it reads shallow. This is exactly the kind of forensic detail that careful geology can extract from what looks, to a casual observer, like an undifferentiated field of mud and rock. Nobody was in the direct blast zone at the moment of the explosion. This was fortune, not management. No alarm had been issued. No monitoring signal had indicated the explosion was coming. The visitors on the boardwalk happened to be far enough away, and quick enough, to get clear. The USGS Yellowstone Volcano Observatory confirmed, in the analysis that followed, that no precursors to the event had been detected by monitoring instruments. The event was captured by seismic and acoustic sensors that had been installed across the park, providing a detailed record of how the explosion developed, among the most thoroughly documented hydrothermal explosions in the park's history. This was scientifically valuable. The dataset would help researchers understand the acoustic and seismic signature of these events, potentially useful in eventually learning what, if anything, precedes them. But the operational reality was stark. The explosion had occurred at a popular tourist feature. The USGS described the July 2024 event as emphatically demonstrating an underappreciated hazard in the Yellowstone region. The USGS explicitly identifies hydrothermal explosions as the geological hazard most likely to impact people in Yellowstone National Park. In the weeks and months after the explosion, scientists from several institutions collaborated to install temporary monitoring stations around Black Diamond Pool, trail cameras, seismometers, acoustic sensors, and electromagnetic instruments. The cameras recorded changes such as newly ejected rocks, and the seismic and acoustic sensors detected dozens of smaller eruptions from the pool in the months that followed. The hydrothermal system, in other words, is not done. Let us slow down and make the underlying physics here concrete. Because the rest of this story depends on understanding a few things precisely: what hydrothermal systems are, how they differ from volcanic systems, and why the specific hazard they represent is so difficult to predict. Think of it this way: imagine a pressure cooker. Inside, Water is heated above its normal boiling point, not because the temperature is not high enough to boil, but because the pressure is high enough to keep it liquid. The sealed lid maintains the pressure, the water stays liquid. If you release the lid suddenly, if the pressure drops abruptly, the water flashes to steam instantaneously. At atmospheric pressure, steam occupies vastly more volume than the water it came from, well over 1,000 times as much. The expansion is explosive. Now, scale that process up to a body of water heated well above its normal boiling point, sitting in fractured rock at depths of tens to hundreds of feet beneath a national park. The rock above it is the lid of the pressure cooker. As long as the rock holds and the pressure stays sufficient, the water remains liquid despite being far above its surface boiling point. But the system is in a delicate equilibrium. The rock can fracture, the water table can change, a blockage in the plumbing can shift, or a small seismic event can suddenly alter the pressure in a specific zone. When that happens, the water flashes to steam faster than any available containment can absorb. The steam drives the rock and water above it upward. You get an explosion, not from magma, from water, from the same physical process that every kitchen pressure cooker demonstrates, at a scale that fits on a countertop. The key insight here is that the energy is already stored in the system, waiting. A body of superheated water held under pressure is, in effect, a loaded spring. It does not need any new input of energy to explode, no fresh injection of magma, no surge of heat from below. It only needs the confinement to fail. The water is already hot enough. It is only the pressure of the overlying rock that keeps it from flashing to steam. Remove or reduce that pressure suddenly, and the transition happens almost instantaneously, releasing energy that had been quietly accumulating for years or decades. This is what makes hydrothermal explosions so difficult to anticipate. There may be no dramatic buildup to detect, because the buildup already happened, slowly, long before the trigger. The trigger itself can be small, a minor shift in the plumbing, a slight drop in the water table, and yet the consequence is enormous, because the consequence was loaded and waiting the whole time. There are 3 things you need to understand to follow what comes next. The first is the difference between hydrothermal activity and volcanic activity. Volcanic activity involves magma, molten rock, moving toward or reaching the surface. The geysers, hot springs, and fumaroles of Yellowstone are not volcanic in this sense. They are hydrothermal, driven by surface water that has percolated down through the crust, been heated by the magmatic system far below, and returned toward the surface through fractures and porous rock. A hydrothermal explosion requires no magma at or near the surface. It requires only hot water, sufficient pressure, and an instability. This distinction matters enormously for hazard assessment and for monitoring. The instruments designed to detect volcanic precursors, seismometers monitoring for deep fluid movement, GPS stations tracking ground deformation associated with magma migration, are not necessarily effective at predicting hydrothermal explosions, which can occur through local pressure changes in the shallow hydrothermal system without any deep volcanic precursor signal. The second is the scale of Yellowstone's hydrothermal system. More than 10,000 thermal features, Yellowstone has more geysers than the rest of the world combined. The thermal output of the entire system is maintained by heat rising from the magmatic system kilometers below. The hydrothermal water circulates through a complex network of fractures, faults, and porous rock, connecting surface features to the deep heat source through pathways that scientists are still mapping. Any of these 10,000 features is, in principle, a potential hydrothermal explosion site. The explosions documented in the geological record have occurred at sites across the park, not just at historically active geysers, but at features that showed no obvious precursory activity. the largest known hydrothermal explosion in Yellowstone's geological record. The Mary Bay event, roughly 13,800 years ago, created a crater complex on the order of 2.5 kilometers across in what is now part of Yellowstone Lake. The scale of the Mary Bay event is worth sitting with. A crater 2.5 kilometers across is not a feature you would casually walk past. It is large enough that, standing at one rim, the far rim would be well over a mile away. An explosion of hot water and rock, capable of excavating a hole that size represents an energy release in the same general league as a significant volcanic explosion. And yet, it involved no magma at the surface at all. It was, in essence, the largest pressure cooker failure in the region's recent geological history. Events on the Mary Bay scale are rare, occurring perhaps once in many thousands of years, but they establish the upper bound of what the hydrothermal system is capable of. The July 2024 Biscuit Basin explosion, by contrast, was a very small event on this spectrum. The geological record makes clear that the system can, on rare occasions, do something vastly larger. The third is what the monitoring network can and cannot do. The monitoring network at Yellowstone is extraordinarily capable at detecting changes in the deep magmatic system. The seismic activity associated with magma movement, the ground deformation associated with inflation and deflation of the magma reservoir, the gas flux changes associated with increased degassing of the magmatic system. These are the signals that would precede any significant volcanic eruption, and the network would likely detect them with weeks to months of lead time. For hydrothermal explosions, the monitoring capability is much more limited. The July 2024 Biscuit Basin event showed no clear precursory signals identifiable in advance. The new monitoring equipment installed afterward is designed to build a baseline, to understand what normal behavior looks like at specific features, so that deviations can potentially be identified. But the general problem of predicting hydrothermal explosions across 10,000 features in a park, the size of a small state, remains unsolved. Here is where the stakes rise in a way that is both personal and geological. Millions of people visit Yellowstone National Park each year. They walk on boardwalks above thermal features. They approach geysers. They photograph hot springs. They do this because the park is one of the most extraordinary natural environments on the continent, and the thermal features are among its defining attractions. They do this in a park whose primary geological hazard, according to the US, is not the supervolcano. It is the hydrothermal system. Hydrothermal explosions are essentially certain to continue occurring at Yellowstone. They have been documented in the geological record for thousands of years. They are a fundamental feature of the system, and there is no reason to expect they will stop. The question is not whether they will happen. It is where, and when, and with how much energy. The difficulty for park management is that this hazard is, in a sense, woven into the very thing that makes Yellowstone worth visiting. The hot springs and geysers that draw millions of people are the surface expression of exactly the pressurized hydrothermal system that occasionally explodes. You cannot have one without the other. The thermal features are not separate from the danger. They are the danger in its quiet, beautiful, day-to-day form. A visitor leaning over a boardwalk railing to photograph a brilliant blue pool is standing directly above the kind of system that, somewhere in the park, on some unpredictable day, will flash to steam and throw rock into the air. Most of the time, in most places, nothing happens. The boardwalks have stood for decades, but the July 2024 event was a reminder that most of the time, and most places, are not the same as always and everywhere. The largest hydrothermal explosions in Yellowstone's past have created craters kilometers across. The Mary Bay event was large enough to affect a significant area around Yellowstone Lake. These are not supervolcanic events. They involve no magma. They do not produce ash clouds that cross continents, but in their immediate vicinity, they are devastating. The July 2024 Biscuit Basin explosion was, in the context of the full geological record, a relatively small event. It was fortunate enough to occur when no visitor was in the direct blast zone. A larger hydrothermal explosion, the kind that occurs at Yellowstone every few thousand years, in a popular visitor area at a busy time of day, would be a very different event. This is the real Yellowstone hazard story, not the supervolcano, the ground beneath the boardwalks. The image that most people carry of the magmatic system beneath Yellowstone is wrong in a specific way. They picture a vast lake of liquid molten rock sitting just below the surface, red and glowing, held back only by a thin crust that could rupture at any moment. This image comes from disaster films, from sensationalist documentaries, from the instinctive human tendency to picture anything called a magma chamber as a seething reservoir of liquid fire. The reality, as revealed by decades of seismic imaging, is more complex and more interesting, and in practical terms, considerably less alarming. Seismic tomography is the technique that has given scientists their best view of Yellowstone's interior. The principle is similar to a medical CT scan. Seismic waves, produced by earthquakes, both at Yellowstone and at more distant locations, travel through the Earth and are recorded by the network of seismometers around the park. The speed at which seismic waves travel depends on the properties of the rock they pass through. In regions where the rock is partially molten, where pockets of magma are distributed through the crystalline rock matrix, seismic waves travel more slowly. By mapping these low-velocity zones, scientists can infer where the partial melt is concentrated. The analogy to a medical scan is worth taking seriously, because it captures both the power and the limits of the method. A CT scanner builds a three-dimensional image of the inside of a body by sending energy through it from many angles and measuring how that energy is absorbed or slowed along each path. Seismic tomography does the same thing for the interior of the Earth, using earthquake waves as its energy source and seismometers as its detectors. The more earthquakes you record, and the more seismometers you have recording them from different directions, the sharper your image becomes. This is why the picture of Yellowstone's interior has grown steadily more detailed over the decades. Not because the interior changed, but because the number of instruments and the volume of recorded data kept increasing. A major deployment of hundreds of seismometers in recent years has refined the image further still. Crucially, this means that when scientists announce they have found a new feature beneath Yellowstone, the right interpretation is almost always that the feature was always there and the scan finally became sharp enough to resolve it, not that something new has appeared. The picture that has emerged from 2 decades of increasingly sophisticated seismic tomography has been refined, extended, and, on one significant occasion, substantially expanded. The magma reservoir, the main feature that most people mean when they say Yellowstone's magma chamber, sits beneath the caldera at depths of roughly 5 to 17 kilometers. It is large, tens of kilometers across in each dimension, but it is not a liquid. The estimated melt fraction, the proportion of the material that is actually molten versus crystalline solid, is in the range of 5 to 15%. The rest is solid rock, interspersed with pockets and films of melt distributed through it, in the way that water is distributed through a wet sponge. To produce an eruption, this mostly solid material would need to become substantially more liquid. The melt fraction would need to increase significantly, a process that requires major heat input from below, which would show up clearly in the monitoring data through seismic changes, ground deformation, and increased volcanic gas output. The process would not be invisible, it would not be sudden. As one summary put it, nearly all of the partly molten rock beneath Yellowstone appears too frozen to erupt, and no one has found evidence that the near-surface magma storage region is growing within the timeframe Yellowstone has been monitored. In 2015, a team led by Jamie Farrell at the University of Utah published a study in Science describing a previously undetected component of Yellowstone's magmatic system, using an expanded seismic dataset and improved imaging. They identified a large body of partially molten rock in the lower crust, beneath the already known upper magma reservoir. This lower crustal body sits at depths of roughly 20 to 50 kilometers and is several times the volume of the upper reservoir. The discovery made headlines. Some outlets reported it as a giant new magma reservoir discovered beneath Yellowstone, with implications of elevated danger. The USGS responded immediately and clearly. The lower crustal body does not change the volcanic hazard assessment at Yellowstone. It does not increase the probability of an eruption. It represents the deep root of the Yellowstone magmatic system, the connection between the hotspot and the shallower magma reservoir that had been there all along, simply invisible to earlier imaging. Crucially, finding more magma than we previously knew about is not the same as the magma increasing. Better imaging revealed what was already there. What the discovery actually tells us is that the Yellowstone system is even more deeply connected to the hot mantle below it than previous imaging had shown. The heat budget that sustains the extraordinary thermal output of the Yellowstone system, the 10,000 thermal features, the thousands of megawatts of heat output, is supplied ultimately from this deep system, fed by the hotspot. This is worth dwelling on, because it is precisely the kind of finding that doomsday coverage loves and routinely misrepresents. The headline writes itself. Scientists find huge new magma body beneath Yellowstone. It sounds like the volcano is loading up to erupt. It is nothing of the sort. The lower crustal body is old, mostly solid, and was discovered not because it appeared, but because our instruments finally became good enough to see it. The title of this very video plays on the same instinct. Scientists just found new magma. And the honest answer is that they did not find new magma so much as a clearer picture of magma that was always there. That distinction is the entire difference between accurate science and a scare story. The same misunderstanding has recurred several times in Yellowstone's coverage history, and it follows a predictable script. A research team publishes an improved image of the subsurface. The image reveals more magma than the previous, blurrier image had shown. A headline announces that the magma reservoir is bigger than thought, or that a new reservoir has been discovered. Readers naturally infer that the volcano has grown more dangerous, and then the USGS has to step in, again, to explain that an improvement in measurement is not a change in the thing being measured. Finding more of something, because you can finally see it clearly, is not the same as that something increasing. If you upgrade from an old pair of binoculars to a powerful telescope and suddenly see far more stars, the sky did not gain stars, your instrument improved. This is almost exactly what has happened repeatedly beneath Yellowstone. The magma was always there, our eyes got better. Below even the lower crustal body, the seismic imaging traces the Yellowstone hotspot into the upper mantle, a region of anomalously low seismic velocity consistent with the upwelling of hotter than normal mantle material. This is the deep engine that has been driving the Yellowstone system for millions of years. And above all of this, above the deep system, above the lower crustal body, above the upper magma reservoir, the hydrothermal system sits in the uppermost few kilometers of the crust, connected to the magmatic heat source below, but operating on its own dynamics, through its own plumbing of fractures and faults and permeable rock. The magmatic system is vast. It is complex. It is genuinely extraordinary. It is also, right now, showing none of the precursory signals that would indicate movement toward an eruption. The is, put it plainly. The annual probability of a volcanic eruption is on the order of 1,000%, and even that low number is probably an overestimate for the short term. The Yellowstone Volcano Observatory is one of the most comprehensive volcanic monitoring operations in the world. It is a consortium that includes the University of Utah seismograph stations, the National Park Service, and several other partner institutions. The consortium coordinates the design, maintenance, and interpretation of a monitoring network that covers the entire Yellowstone region. The seismic network is the backbone. Roughly 50 seismometers are distributed across the Yellowstone region, operated by the University of Utah. They record ground motion continuously, day and night, year-round, and the network is sensitive enough to locate very small earthquakes, far too small to be felt, giving scientists a detailed picture of where the crust is fracturing, where fluids are moving, and where stress is concentrated. Yellowstone averages 1/500 to 2/500 located earthquakes per year, most of magnitude 2 or below, often occurring in swarms that reflect fluid movement through the hydrothermal system and crustal fracturing rather than magmatic activity. The ground deformation network is the second essential component. Continuous GPS stations distributed across the park and surrounding region record the position of the ground beneath them to millimeter precision. By analyzing how those positions change over time, scientists map the deformation of the caldera, where it is inflating, where it is subsiding, at what rate, and with what spatial pattern. The caldera floor has inflated and subsided repeatedly since systematic measurement began. The mechanisms are complex, involving the injection and withdrawal of magma and hydrothermal fluids in the crust. The volcanic gas monitoring network provides a third independent view. Carbon dioxide and hydrogen sulfide are produced when magma degasses. By measuring the flux of these gases, scientists can track changes in the degassing behavior of the magmatic system. An increase could indicate increased magmatic input. The infrasound and acoustic network is a more recent addition. These sensors detect very low-frequency sound waves that travel efficiently and can detect energetic events, including geyser eruptions and hydrothermal explosions. This network has been expanded in recent years, and the new equipment installed at Biscuit Basin following the 2024 explosion represents an investment in specifically improving the monitoring of hydrothermal features. Together, seismic, deformation, gas, and acoustic, plus satellite thermal imaging, these systems constitute one of the most detailed real-time monitoring operations for any volcanic system on Earth. What do they currently show? In short, normal Yellowstone, background seismicity, ground deformation within the documented range, gas fluxes within long-term norms, steamboat, geyser, continuing intermittent activity, black diamond pool in Biscuit Basin, continuing active but not unusual hydrothermal behavior. The USGS alert level is normal. The aviation color code is green. There is no sign of elevated volcanic activity. But there is a question the monitoring data, for all its sophistication, cannot yet fully answer. What would the instruments show in the hours before a hydrothermal explosion? The July 2024 Biscuit Basin event provided the first real data on this question, and the answer was sobering. Almost nothing identifiable as a precursor appeared in the instruments before the explosion happened. This is the crux of the prediction problem, and it deserves to be stated plainly. For a magmatic eruption, the supervolcano scenario that dominates the headlines, the monitoring network is genuinely powerful. Magma cannot move toward the surface without announcing itself. It cracks rock as it rises, producing distinctive earthquake swarms. It pushes the ground upward, producing deformation the GPS network can measure. It releases gas, which the gas sensors can detect. These signals would build over weeks to months, giving ample warning. The irony of Yellowstone is that the hazard everyone fears is the one we would see coming most clearly. But for a hydrothermal explosion, the hazard most likely to actually hurt someone, the warning signs may be minimal or absent, because, as we have seen, the energy is already stored and the trigger can be small and shallow and sudden. The network that would give months of warning for a supereruption gave essentially no warning for the Biscuit Basin explosion. That asymmetry between the predictable rare catastrophe and the unpredictable common hazard is one of the most important and least appreciated facts about living alongside Yellowstone. Here is the hazard spectrum at Yellowstone, presented in the order that matters most, from highest probability to lowest. This is an order that almost no popular Yellowstone coverage uses. Popular coverage almost always presents the hazards in reverse, beginning with the supereruption because it is the most dramatic, proceeding to smaller eruptions as a concession to accuracy, and either omitting the more probable hazards entirely or mentioning them briefly at the end. The result is a wildly distorted picture of where the actual risk lies. The highest probability hazard at Yellowstone is hydrothermal explosions. They have been occurring for as long as the hydrothermal system has been active, and the geological record contains many of them, including at least a dozen that created craters larger than 100 meters across. They are not volcanic. They do not signal magmatic unrest. They are an inevitable consequence of maintaining a large body of superheated water in a fractured, permeable crust, and they cannot, at present, be reliably predicted. The second highest probability hazard is earthquake activity. Yellowstone is seismically active by any standard. The 1959 Hebgen Lake earthquake, magnitude 7.3, was among the most powerful to strike the contiguous United States in the 20th century. It triggered a landslide that killed 28 people and created what is now Earthquake Lake in Montana, and it permanently altered hydrothermal features across the park. Future, large earthquakes in the region are geologically expected. The Hebgen Lake earthquake is worth remembering in some detail, because it is the clearest demonstration that the seismic hazard at Yellowstone is not hypothetical. It struck late at night in August 1959, just northwest of the park. The shaking dislodged an entire mountainside, sending tens of millions of cubic meters of rock down into the Madison River Canyon, where campers were sleeping. The landslide buried part of a campground and dammed the river, drowning the valley behind it to form the lake that still bears the event's name. 28 people died. And across the park, the earthquake rewired the hydrothermal system. Some geysers that had been dormant sprang to life, others that had been reliable went quiet, and the plumbing connections beneath the surface were rearranged in ways that persisted for years. It was a vivid reminder that Yellowstone's seismic and hydrothermal systems are coupled. A large earthquake does not just shake the ground, it can reach into the hydrothermal plumbing and change how the whole surface expression of the system behaves. Earthquakes of this size are infrequent, but they are an established part of the region's behavior, and the faults capable of producing them are still there. The third significant hazard, and the one most directly volcanic, is the possibility of future volcanic activity, not a supereruption, but smaller events. The USGS emphasizes that the most likely form of future volcanic activity, if any occurs on human-relevant timescales, would be a lava flow, rather than an explosive eruption. The most recent volcanic eruption at Yellowstone was a lava flow, roughly 70,000 years ago. Future lava flows, if they occur, would be preceded by extensive precursory activity, seismic swarms, ground deformation, gas changes, clearly visible in the monitoring network with weeks to months of lead time, allowing orderly evacuation. And finally, at the bottom of the probability ladder, there is the supereruption. Annual probability, roughly 1 in 1730 zows. To put this in context, that is comparable to, or lower than, a range of natural hazards we rarely lose sleep over. The USGS notes the magmatic system is mostly solid. There are no signs of elevated activity, and a supereruption is the least likely volcanic scenario for Yellowstone. The agency has gone so far as to say that scientists are not convinced another supereruption will ever happen at all. If a supereruption were to occur, the consequences would be severe by any measure. Thick ash across much of the central and western United States, disruption of agriculture across the continent, global temperatures declining by several degrees for years. The disruption would affect hundreds of millions of people, but civilization ending. The science does not support that characterization. Modern civilization has survived large volcanic eruptions, including the 15 Tambora eruption, the largest in the past 2,000 years, which caused the year without a summer in 1816 and widespread crop failures, but did not end civilization. A Yellowstone supereruption would be much larger than Tambora, but the global infrastructure, agricultural reserves, and response capabilities of the modern world are also far greater than those of 1816. Even previous Yellowstone supereruptions did not cause mass extinctions. It is worth being precise about what catastrophic but not civilization ending actually means, because the distinction is not a comforting technicality, it is a real and important difference. A Yellowstone supereruption would be one of the worst disasters in human history. It would bury large portions of a continent in ash, ground air travel across much of the world, disrupt agriculture globally for years, and cause economic damage that is difficult to even estimate. Hundreds of millions of people would be affected. None of that is being minimized here. But the worst disaster in human history and the end of human civilization are different claims, and the evidence supports the first while not supporting the second. Humanity has weathered global volcanic disruptions before and emerged intact. The fossil and archaeological record shows our species surviving even larger events in the deep past. Civilization is more fragile than we would like, but also more resilient than the doomsday framing assumes. The honest message is neither a nothing to worry about, nor the end of the world. It is a genuine catastrophe of low probability, which we should understand clearly rather than either dismiss or catastrophize. The end of civilization framing is not scientifically supported. The hazard is real. The consequences would be catastrophic by any normal standard. The probability in any human lifetime is very small. This is the actual Yellowstone hazard picture. Hydrothermal explosions, ongoing, certain, to continue, unpredictable. Earthquakes, ongoing, large events possible, lava flows, possible, with significant precursory warning, supereruption, real but vanishingly improbable on human timescales. The scenario that fills the headlines is at the bottom of the list. The scenario most likely to actually affect a visitor to the park happened in July 2024. And now, we should deal directly with the word in the title of this very video: overdue. The idea that Yellowstone is overdue for an eruption is one of the most persistent and most thoroughly debunked claims in all of popular geology. The reasoning behind it goes like this. Yellowstone has had 3 supereruptions, roughly 1 million, 3 million, and 64 million years ago. The gaps between them average around 725,000 years. It has been about 640,000 years since the last one. Therefore, the argument goes we are approaching, or have passed, the due date. The USGS has addressed this directly and bluntly. In their words, overdue can apply to library books, bills, and oil changes, but it does not apply to Yellowstone. There are several reasons the reasoning fails. First, even if you took the average interval at face value, the math does not make Yellowstone overdue. By that average, there would still be roughly 100,000 years to go. The title's 1,000 years overdue framing has no scientific basis at all. Second, and more fundamentally, you cannot establish a reliable cycle from just two intervals between three events. Two data points are not a pattern. Third, and most fundamentally of all, volcanic systems do not run on schedules. Most volcanic systems that produce one supereruption never produce another. When they do produce more than one, the eruptions are not evenly spaced in time. The entire premise of a due date misunderstands how these systems behave. Consider how absurd the overdue logic would sound applied to almost anything else governed by chance, rather than schedule. Imagine claiming that, because a particular stretch of coastline has been hit by major hurricanes roughly every few decades on average, it is now overdue, and a hurricane is therefore imminent. The atmosphere does not keep a calendar, neither does the Earth's crust. An average interval, computed from a handful of past events, tells you something about the long-run rate of a process, but nothing about when the next event will occur. A system can sit quietly for far longer than its average gap, or produce two events in quick succession, without violating any statistical rule, because the events are not scheduled. They are the product of physical conditions that have to be met. At Yellowstone, those conditions are not currently met. The magma is mostly solid. There is no large body of eruptible melt poised to erupt. Whatever the averages say, the physical state of the system is the thing that actually matters, and the physical state says, not now, and not for a very long time, if ever. There is one more layer to this. The USGS has explicitly noted that scientists are not even convinced there will ever be another supereruption at Yellowstone. The hotspot is a finite engine in a slowly changing configuration, and there is no law that says it must produce another caldera-forming event before it moves on. The popular framing treats a fourth supereruption as inevitable and merely a matter of timing. The science treats it as possible but uncertain. Something that may or may not ever happen, and that, if it does, lies most likely far beyond any timescale relevant to us or to many generations after us. So, when you see a headline saying, Yellowstone is overdue, including, in a sense, the headline of this very video, you are looking at a claim that the scientists who study Yellowstone most closely have explicitly and repeatedly rejected. We put it in the title because it is the claim you have almost certainly heard. We are telling you, plainly, that it is wrong. There are three ways to think about what Yellowstone's current state and geological history mean. The conservative interpretation is that Yellowstone is in a normal intereruptive phase. The monitoring system is working, and the real hazards are being managed as well as current science permits. The monitoring network tracks background seismicity, measures ground deformation, monitors gas flux. The system is at normal because it is, by every available measure, in a normal state. The July 2024 explosion was significant, but did not change the volcanic hazard assessment. The supporting evidence is the USGS' own assessment, and the decades-long record showing no approach to a magmatic eruption. The weakness is that normal Yellowstone still includes events like the 2024 explosion that the monitoring cannot predict. The moderate interpretation is that hydrothermal hazards are underappreciated relative to the volcanic scenario, and that the July 2024 explosion demonstrated real prediction gaps. The correct response is increased monitoring targeted at hydrothermal features, better understanding of any precursory signals, and visitor management protocols that account for the spatial distribution of hydrothermal explosion risk. This is the view most clearly supported by the data. Given the USGS' own characterization of hydrothermal explosions as the most likely hazard to affect people, the bold interpretation is that Yellowstone's significance extends far beyond its hazard potential, that it is one of the most extraordinary windows into the deep geology of a continent, and deserves to be understood and communicated not primarily as a threat, but as one of Earth's most remarkable active geological systems. The 17-million-year hotspot track is as scientifically important as the caldera itself. The hydrothermal system is a working model of processes that may occur on other planetary bodies, and Yellowstone's position as both a geological wonder and a public land visited by millions makes it one of the most important interfaces between Earth science and public understanding anywhere in the world. Here is what is worth saying before we leave the interpretive landscape. Yellowstone does not threaten civilization because it wants to, it simply is. It is doing what it has done for millions of years, drawing heat from deep in the earth, maintaining an extraordinary hydrothermal system, breathing in and out as fluids pulse through its crust, occasionally erupting in ways that range from a geyser column to a hydrothermal explosion to, separated by hundreds of thousands of years, a supereruption. The scientists who watch it most carefully, the ones who have spent careers learning to read its signals, are not afraid of it, they are fascinated by it. There is a lesson in that difference. After everything we have seen, the hotspot track, the 3 supereruptions, the July 2024 explosion, the monitoring network, the magmatic system, the real hazard spectrum, here is what we now know, and what we still do not. We know Yellowstone sits above one of the most powerful and complex magmatic systems in North America, fed by a hotspot that has been operating for millions of years. We know the system is currently at background levels, with an annual supereruption probability of roughly 1 in 730 ZOWs. We know hydrothermal explosions are real, ongoing, and the geological hazard most likely to affect park visitors, demonstrated emphatically by the July 2024 Biscuit Basin event. We know the monitoring network, for all its sophistication, did not predict that explosion. We do not know what, if any, detectable precursors reliably precede hydrothermal explosions. We do not fully understand the cause of the recent North Caldera Rim uplift episode, and we cannot say precisely what Yellowstone will do over the next tens of thousands of years. That is where the science currently sits. Here is the strange thing about how Yellowstone has been covered in popular media. The coverage follows a remarkably stable pattern. A new paper is published, or a swarm of earthquakes is detected, or a geyser changes behavior. The story gets framed as the supervolcano, and the inevitable question is raised: is it about to erupt? The scientists say no, the story fades, nothing happened. A few months later, the cycle repeats. This pattern has several problematic consequences. The first thing the headlines have consistently missed is the July 2024 hydrothermal explosion, an explosion in a popular tourist area, thoroughly documented, that destroyed visitor infrastructure and would have been dangerous to anyone in the blast zone. The hazard, the USGS identifies as most likely to affect people in the park. This is essentially absent from the popular Yellowstone hazard narrative. The second is the actual probability context for the supereruption, 1 in 730 ZOWs per year, an estimate the USGS calls probably an overestimate for the short term, from an agency that says it is not convinced another supereruption will ever happen. These official assessments are routinely absent from or underemphasized in popular coverage. The third is the overdue framing, which, as we have seen, the USGS has explicitly and repeatedly rejected, and which appears in popular coverage so consistently that many people have absorbed it as fact. The fourth is what Yellowstone actually is geologically, the 17-million-year hotspot track, the Snake River Plain as its scar. The fact that Yellowstone is the latest chapter of a process that began near the Nevada-Oregon border. This essential context is almost never part of popular coverage. The fifth is the genuine scientific value of the monitoring program. The science being done at Yellowstone, on magmatic system dynamics, on hydrothermal behavior, on seismic precursors, on the relationship between deformation and fluid movement, is important well beyond its immediate hazard relevance. Popular coverage rarely engages with it. It asks only whether the volcano is about to erupt. In the months since the July 2024 explosion, the monitoring picture has continued to evolve. The most significant ongoing development is the post-explosion monitoring program at Biscuit Basin, where the comprehensive equipment installed after July 2024 has been building a baseline understanding of the basin's behavior. Black Diamond Pool, the feature that exploded, has continued to produce smaller eruptions, recorded by the new instruments, continued active but not unusual hydrothermal behavior. The second development is the North Caldera Rim uplift episode that began in mid-2025 and ceased in early 2026, without transitioning to the subsidence that typically follows. The USGS has described this as a subtle change in the style of caldera deformation, consistent with normal variation in the system's fluid dynamics rather than a precursor to elevated volcanic activity, but a detectable change in behavior that the scientific community is watching. It is instructive to watch how the USGS handles a finding like this, because it models exactly the kind of careful, non-alarmist reasoning that good hazard science requires. The uplift was real and measurable. It was also unusual in that it did not follow the typical pattern of being followed by subsidence. A doomsday-minded interpreter would seize on the words unusual and uplift and spin a story about the caldera awakening. The USGS instead does something more disciplined. It notes the observation precisely, places it in the context of decades of documented deformation, offers the most probable mundane explanation, ordinary variation in the movement of underground fluids, and commits to continued monitoring without either dismissing the observation or inflating it. This is what it looks like to take a system seriously without fearing it. The behavior is logged, studied, and kept in proportion. That posture, curious, attentive, unafraid, is the posture the whole Yellowstone story rewards. The third development is the broader research program the 2024 explosion catalyzed. Field investigations of geyser activity, new deformation equipment, geochemical sampling, and an updated YVO hazard response plan that, reflecting the lessons of 2024, addresses hydrothermal explosion scenarios explicitly and acknowledges that hydrothermal explosion prediction remains limited. The fourth development worth noting is the continuing activity of Steamboat Geyser at Norris, the world's tallest active geyser, capable of eruptions reaching some hundreds of feet. After reactivating with high frequency in 2018, its rate of major eruptions has declined in recent years. Norris is one of the most dynamic and least fully understood thermal areas in the park, and changes there are watched closely. And here is what makes the Yellowstone story truly remarkable. Not the supereruption, which is real but distant, not the doomsday scenario, which is technically possible and practically improbable, not the statistics, which are important but cold. What makes Yellowstone remarkable is what it actually is. Below the geysers, below the hot springs and the boardwalks and the bison herds and the tourists photographing Old Faithful, below the Grand Canyon of the Yellowstone and the dark forest and the rivers that drain the caldera. The ground is breathing. It has been breathing for millions of years. Before it was breathing under Wyoming, it was breathing under Idaho. Before that, near the Nevada-Oregon border, The column of anomalously hot mantle that drives it has been feeding heat upward through the crust in a process that makes the slow, vast tectonic activity of continents visible on something closer to human timescales. The three supereruptions at Yellowstone are not evidence that the system is dangerous. They are evidence that the system is powerful. That distinction matters. Everything powerful is not necessarily dangerous to us. The sun is unimaginably powerful. It is also what makes life on Earth possible. Yellowstone is not trying to end civilization. It does not try anything. It is doing what it has done since before our species existed, and what it will do long after our species is gone, moving heat upward, maintaining a hydrothermal system of extraordinary complexity, occasionally producing events that, on human timescales, range from spectacular to lethal. Let that sit for a moment. Millions of people per year walk across the floor of a volcanic caldera formed by one of the largest eruptions in the history of this continent. They walk in a national park above a geological engine that has been running since before our ancestors were recognizably human. They photograph hot springs that are literally windows into the thermal energy of the Earth's interior. Most of them have no idea that any of this is true, and the scientists who watch it, who have spent careers learning to read its signals, who built the monitoring network that captured the July 2024 explosion in unprecedented detail, are not afraid of it. They love it. There is something clarifying about a geological system that is too old, too large, and too indifferent to be controlled. It reminds you of where you actually are, not on a stable, permanent platform, on a living planet, in an active crust, above a churning mantle, a thin film of creatures on the surface of a world that has been remaking itself for 4.5 billion years, and will keep doing so long after the last human is gone. We tend to experience the ground as the very definition of stability, solid ground, a bedrock, the things we reach for as metaphors for permanence and safety. Yellowstone quietly dismantles that assumption. Here, the ground rises and falls by measurable amounts from year to year. The water in the springs is hot enough to kill. The features rearrange themselves on timescales short enough that a hot spring your grandparents photographed may not exist in the same form today. And beneath all of it, the slow churn of the mantle continues, utterly unconcerned with the national park drawn on the surface or the millions of people who visit it. To stand at Yellowstone with this understanding is to feel, briefly and vividly, the truth that the solid Earth is not solid and not permanent, that it is a dynamic, living system, and that our sense of the ground as fixed is a kind of useful illusion that holds only because human lives are short compared to geological time. That is the Yellowstone secret, not the eruption, the age of what is beneath you. But there is one more piece to this story, because Yellowstone is not the only supervolcano in the world, and it is not the only one that sits beneath a populated area. There is another caldera, smaller than Yellowstone, but showing signs of unrest that Yellowstone is not currently showing. Signs that have prompted the evacuation of tens of thousands of people, that have generated serious scientific debate about what is happening in the magma system below, and that sit beneath a metropolitan area of nearly 3 million people in one of the most historically significant cities in the world. It is called Campi Flegrei. It is beneath the suburbs of Naples, Italy, and what it has been doing over the past decade, the uplift, the seismic swarms, the ground deformation that has cracked buildings and changed the coastline, is a story that deserves a video of its own. That is next time. Tonight, we did not just learn about a supervolcano. We watched what happens when one of the most geologically active systems in North America is seen for what it actually is, not as the backdrop for a doomsday scenario, but as an extraordinary, ongoing, genuinely fascinating piece of the living Earth. We saw the July 2024 Biscuit Basin explosion, a hydrothermal explosion from Black Diamond Pool in a tourist area, without warning, captured by instruments in unprecedented detail, which destroyed boardwalks and would have been deadly to anyone in its direct path. A reminder that the hazard most likely to affect a visitor to this park is not the one that fills the headlines. We traced the hotspot track across millions of years of North American geology, from the Nevada-Oregon border through Idaho to Wyoming, each older caldera, a mark on the continent of where this engine was before. We looked at the actual hazard spectrum: hydrothermal explosions first, earthquakes second, and the supereruption at the bottom, with a probability comparable to a range of hazards we rarely think about. And we dealt honestly with the word overdue, a word the scientists who study Yellowstone have explicitly rejected, a word that appears in this video's own title, precisely so we could tell you why it is wrong. At the end, we arrived at what Yellowstone actually means, not a threat waiting to happen. A geological engine that has been running since long before our species arrived, doing what such engines do, drawing heat from the deep earth, maintaining a system of extraordinary complexity and beauty at the surface, and occasionally reminding us, in explosions both large and small, that we are guests on a planet that was not made for us. There are a few things worth taking from this story that go beyond Yellowstone. The first is that the most dangerous sounding scenario is rarely the most likely one. The supereruption dominates the public narrative. The hydrothermal explosion is the hazard most likely to actually affect a visitor. Understanding the difference between headline risk and real risk is essential for thinking clearly about geological hazards, and about many other kinds of risk. The second is that monitoring investment is risk management. The acoustic and seismic network that captured the 2024 explosion in detail exists because of decades of investment in monitoring that was not motivated by any immediate crisis. That investment is what made the explosion scientifically valuable rather than merely destructive. The third is that overdue is not a scientific concept for volcanic systems. Geological systems do not follow schedules. The language of overdue belongs to popular coverage, not to scientific assessment. The fourth is that geological time requires a different kind of thinking. The 640,000 years since the last supereruption feels long. On the scale of the hotspot's 17 million year history, it is a brief pause. Living thoughtfully with geological hazards requires holding both timescales, the human and the geological, in mind at once. And the fifth is this: the scientists who know Yellowstone best are fascinated by it, not frightened of it. That is not naivety. It is the product of genuine understanding. The more clearly you see what Yellowstone is, the more interesting it becomes. The doomsday framing is not just inaccurate, it is a missed opportunity to tell a story that is far more extraordinary. So, I want to leave you with a few questions tonight. What does it mean to build a national park on the floor of one of the largest volcanic calderas in North America? To make one of the most geologically active places on the continent into a destination for millions of visitors per year? What responsibility does that create, and who bears it? When a hydrothermal explosion destroyed the Biscuit Basin boardwalks in July 2024 without warning, nobody died. Was that good luck? Good management? Both. And what would change if the next explosion happened at a busier site, at a busier time of day? And, at the largest scale, what does it mean to live on a geologically active planet, above processes that operate on timescales that make human civilization look like a single morning? Is that terrifying, or is it, somehow, the most clarifying perspective available to us? Sit with those questions. They are not rhetorical. They are the questions Yellowstone has been asking for millions of years. If this story stayed with you, tell me in the comments, which moment was the one that pulled you in? Was it the July 2024 Biscuit Basin explosion in a tourist area without warning? The hotspot track across the American West? The actual hazard spectrum showing the supereruption at the bottom of the probability list. The debunking of the overdue myth, or the closing realization that the scientists who watch Yellowstone most carefully are fascinated by it rather than afraid of it, and what that says about how we should relate to the geological world we live in. I want to know, and if you want more stories like this, real Earth science, told honestly without the doomsday framing, subscribe to Galaxy Pulse. We go beyond the headlines every single time. I will see you in the next one, below the geysers, below the hot springs and the boardwalks and the tourists. The ground is breathing. It has been breathing for millions of years. It will keep breathing long after everyone reading this is gone. We did not make it. We cannot stop it. We can only try to understand it, and that, it turns out, is more than enough to spend a life.